faster for me. Okay. Okay, for the sake of a video, we're trying to approximate a given function f of x by a function of this form, which is a polynomial of degree n, where these polynomials of each of degree j are specified up front, and we just need the coefficients. And the goal in selecting this approximation is to minimize the norm of the error. So it's the best approximation in the sense of making this measure of magnitude of the error as small as possible. Which measure of the error, because there are many possible norms, the choice we're going with is the L2 norm, or simply 2 norm. So we want the integral, the square root of the integral of the square of the difference to be as small as possible. And that's why this is called a least squares approximation, since we want the integral of a square to be as small as possible. And okay, yeah, so that's our choice because it's differentiable. So we solve this like any other minimization problem in multivariable calculus. And okay, so the coefficients satisfy what is called the normal equations. But to make the normal equations as simple as possible, and also to have a better condition system to solve, we use orthogonal polynomials. So here we don't use these. This is a monomial basis. That's actually a bad choice. If we find polynomials that are orthogonal, meaning that inner products of different polynomials among each other are equal to 0 to make them orthogonal, then these are the coefficients. So we can just compute these relatively quickly. As part of this recap, the inner product of two functions is defined to be the integral of their product. One of them has to be complex conjugated. So if f and g are real, we're just taking the integral of their product. And there may be a weight function included, or in some cases, the weight function will simply be 1. But either way, it has to be positive. So that's how we can define what it means for functions to be orthogonal. So the last thing I established on Monday was that if we can make these polynomials orthogonal, then the coefficients are easy to obtain. So that's what we go with in finding these best approximations in the 2 norm sense. So where I left off was we now need to be able to find polynomials that satisfy this. So that's the first thing I'm going to do now. Here are some examples of orthogonal polynomials of different intervals and different weight functions. But now what I'll do is show you how to construct them in general. Okay. So sequence of monic polynomials where the pairwise inner products are equal to 0 when I is not equal to j. and each polynomial pj is of degree j. Now, who remembers what it means for a polynomial to be monic? Anyone? Okay. A polynomial is monic if the, leading coefficient is equal to 1. Okay. So there are different ways of normalizing these things. This is a convenient normalization for us because that tells us right away what the first one is. P0 of x has to be degree 0, must be a constant. Because it's also monic, that constant has to be 1. So right away the sequence is at least started. All right. Okay. So now how do we continue? We use this process that you may have seen as an undergrad in a linear algebra class. Does this ring a bell for anyone? Graham-Schmidt orthogonalization? Okay. All right, so what I'll do, in case this might ring a bell for anyone, is so in general, if you're given the vectors v1, v2, okay, my subscripts are missing, v1, v2, and so on, that are at least linearly independent. That I know you've seen at one time or another just means that, if you've forgotten, there's no linear combination of these that gives you 0 except to set all the coefficients equal to 0. Or in other words, no vector is a linear combination of any of the others. So you can make them orthogonal. So you need to use a different letter here. U1, U2, and so on. So how you generate these is by this formula. Each new, well, first, U1 is just equal to V1. And then each new U vector has to be generated in such a way that it is equal to, it is orthogonal to all the rest. So you set each new U equal to the corresponding V, and then you subtract off several terms that make it, okay. Actually, instead of simply giving this to you, to try to have a linear combination of a previous, wait, sorry, I need U here. So each new U is equal to the corresponding V, subtracting off multiples of a previous orthogonal vectors in such a way that this new vector is orthogonal to all the previous u's. So we have to select these coefficients. All right, so that uj is orthogonal to ui. So that way, each new vector is orthogonal to all the previous ones, thus making the entire sequence of u's orthogonal. So how do I do that? All right, so to obtain, I'll use a different index here, ck. We'll take the inner product of this formula with uk. So then I have uk, uj, and then take the inner product of both sides of this. With uk. Okay. All right. And we want these to be orthogonal. Okay. Now keep in mind, k goes from 0 up to j minus 1. So there's an implicit assumption here that k is strictly less than j. Now, therefore, these are supposed to be orthogonal because the indices are different. Therefore, this inner product has to be 0. But I can use the different properties of the inner product that I discussed last time. So now I have inner product of uk with vj. Minus, and by the linearity of the inner product, I can pull out the sum and the coefficient. So I have the inner product of uk with ui. Okay. Now, can anyone tell me, how does this expression here drastically simplify? Well, I'll give you a hint. This first part, can't do anything with that. That's going to stay the same. But how does this simplify? And keep in mind, the u's are supposed to be orthogonal, and keeping in mind what that means. Using information that's currently on your screen. Are using this notion of orthogonality applied to the U's. The U's are meant to be orthogonal.
So since I doesn't go all the way to J, that's just 0, right? Or no?
Okay, there is something 0 here. So okay, what we know, the I goes up to from 0. I is less any index less than J, and K is also any index less than J. So both I and K are within this range.
So what if we set I and K equal to each other? Maybe?
Okay. And the reason is?
Because then we're taking the inner product of itself, right? Or
Yes.
yeah.
Okay, so so we're gonna have the term for which I is equal to K. And what happens to all the other ones?
The rest are 0.
Yes, because of this. Because they're orthogonal. So the orthogonality of all the U's up to this point, I mean, UJ is the new one, but K and I have lesser indices. These are already made to be orthogonal. Therefore, and I think, Walker, is what you were getting at, is that the reason you said I equal to K is because all the other terms went away. Due to their being orthogonal. So, so what that means, we're just going to be left with, where's the end of this thing? CK inner product of UK with itself. Now, I've only assumed that the U's are orthogonal, not orthonormal. If they were orthonormal, this would be 1, but we're not going to assume that here. So now we have a formula. So all of this must be equal to 0 way over here. So now we can use that to solve for CK. What's CK?
CK would be, if we moved it, we'd have to divide the UK over. So negative UK comma VJ over UK comma UK.
Oh, you're so close.
Oh. Let me put it on my paper, see what I'm missing.
Well, I'm going to put another equals 0 over here.
Yeah, I was trying to do it in my head, but sometimes that goes bad, so.
Okay.
Actually, oftentimes that goes pretty bad. Let's see. Oh, it should be positive, not.
Yes.
Yeah.
Moving it to the other side.
All right.
Okay. Now we have UK VJ. All right. And now this, we've actually seen this formula already from Monday. I'll just scroll up to that real quick. Yeah, this formula right here, it's the same idea, where the phi's are orthogonal, and you're trying to express, F as linear combination of them. So it works out to be the same kind of formula. So it's like what you're doing is you're expressing VJ as a linear combination of all the U's, but then you want to subtract off the contributions to VJ of your previous orthogonal vectors to get a new vector UJ that's orthogonal to all the rest. Okay, so So another way of looking at it, the new orthogonal vector uj is obtained by subtracting from vj the orthogonal projection of vj, whoops, should be lowercase, onto this subspace spanned by all the previous orthogonal vectors, u1 up to u k minus 1, or j minus 1. Okay. So because what we see here is we're expressing, or up here, if I fill in this formula right here, we're expressing vj in terms of all the previous orthogonal vectors. You take that out, and you get the new orthogonal vector. Okay, so that's the way you take a sequence of non-orthogonal vectors and make them orthogonal. So I want to use the same idea to get new orthogonal polynomials. So now let's assume that we have polynomials p0, p1, and so forth up to pj minus 1. Then we have a following, pj of x is equal to, so now all of these are degrees equal to their indices. So pj is of degree j, these are of lower degree. So what I want to do is, I want to take a polynomial of degree j, put it here, and then subtract off multiples of earlier p's. So what exactly will I orthogonalize? I can put any polynomial of degree j here, but a convenient choice is this one, x times pj minus 1 of x. Because this is of degree j minus 1 multiplied by x bumps the degree up to j. Then I have a sum like before of these ratios of inner products. So p I x p j minus 1 over pi and all that's multiplied by pi of x. So this is how I get each new monic orthogonal polynomial from the previous ones. Because if pj minus 1 is monic already, I multiply it by x with its coefficient of 1. The product also is monic. And because this is of lower degree, so this won't mess with the monicness of this part. Okay. So this is how I generate my sequence of orthogonal polynomials. So here, this xpj minus 1 that you see here and here, that's the vj. The pi's play the role of the previous orthogonal vectors. So this is Gram-Schmidt for any kind of vector and inner product you choose. Here I'm using polynomials as my vectors, and my inner product is some kind of integral, like I showed last time. So any questions at this point? Good, because now here's where things get really freaky. If we look at this inner product from a numerator, pi x p j minus 1. Well, I can rewrite that as xpi times with pj minus 1. And I'll recall the definition of our inner product. Okay, well, okay, for real valued functions f and g, then we have okay. So given this definition of inner product, okay, we have an optional weight function here. I'll just throw in. Okay. But that doesn't really matter here. Given this definition, can anyone tell me why this is valid? Why is it I'm allowed to do this? Look what's going on here when we compute this inner product. We take whatever's here, it's all multiplied together. So if I look at this, I have pi x pj minus 1, it's all multiplied together. B's here, also multiplied together. But multiplication being commutative at all, doesn't matter whether the x sits here or here if they're all being multiplied together. So that's why I'm able to do that. Question is, why would I do that? What do I gain by doing that? Looked at this way, is the inner product of xpi, which has degree I plus 1, with pj minus 1, which is of degree j minus 1. However, each p is orthogonal to all previous polynomials but because it's orthogonal to all of these guys, it's orthogonal to any linear combination of them. So what we could say is something stronger. pk is orthogonal to all polynomials of degree less than k. So, given this, each one of these p's is orthogonal to all polynomials that have less degree than itself. What does that tell me about this inner product right here of polynomials of these degrees? because we have this expression for PG already, but the point is, in what way does this expression simplify considerably because of what we see here?
Is it something to do with the definition of orthogonal?
Yes.
So maybe equaling 0?
It does equal 0 under a certain condition based on relating I and J.
Well,
Based on what's said here.
I guess J being one more degree than I.
Almost. What has to happen is, because PG minus 1 is orthogonal to all polynomials of less degree than itself. Therefore, this degree has to be less than this, which might have been what you were getting at, but the statement that you made was quite close. Okay. So what that means is, okay, this inner product, let's see, where did I put it? So this inner product is equal to 0 if I plus 1 is less than j minus 1, or if I take this plus 1 and move it to the other side, then I have I is less than j minus 2. So these coefficients here, most of them are 0. How many of these are non-zero because of this condition here? So if all of these go away, how many are left? Because I is starting from 0 and going all the way up to here.
Just one?
Almost.
Oh, so it's j minus 1 and j minus 2 because it's not less than or equal.
Yes,
Okay.
I thought to suggest
So 2.
that.
Yeah.
All right, very good. Yeah, so each new polynomial, Pj, depends only on the previous two. Okay. So Pj of x is equal to, I can write it this way, x minus, I want to check my notation from the book to make sure it's consistent. Okay, x minus alpha j times p j minus 1 minus beta j minus 1 squared. Oh, whoops, I forgot the of x. Okay. J minus 2 of x. So we have these coefficients, alpha j and beta j minus 1 squared, where alpha j is equal to, so we take this coefficient. For a case where I is equal to j minus 1, that's the alpha. Now I just need to find that number code here. Okay. Okay, and for this case, I is equal to j minus 1, so I need to put that in here. Okay. And then, so because what I have here is, here I have x times pj minus 1. And then I also have this coefficient times pj minus 1 for a case of I equal to j minus 1. So I just lump those two terms together. And then I have a case of I equal to j minus 2. So then I'll have this coefficient when I is equal to j minus 2 times p minus 2. So I need to fill that in now. So that's beta minus 1 squared is equal to, all right, so the same coefficient when I is equal to j minus 2 okay. All right. Now, notice here, look at my indices. I just have j minus 1 and j minus 2 everywhere. That's a lot of minuses. What I'm going to do is I'm going to increase all of the indices on both sides of this equation by 1. So I had just to clean up a little bit. So it's beta j, and then I increase all of these. Okay. All right. So what I can tell you is that from all those coefficients, or other coefficients being 0, this is called a 3-term recurrence relation. Whoops. Okay. Each polynomial depending on the previous 2. Where have we seen that kind of relation before? A sequence of somethings where each something depends on the previous 2 somethings.
Was it Chebyshev?
Yes. Each Chebyshev polynomial depends on the previous 2. But as I mentioned on Monday, the Chebyshev polynomials are an example of orthogonal polynomials on the interval -1 to 1 with a certain weight function. So that 3-term recurrence that you're familiar with for Chebyshev polynomials is a special case of this, where you just have the integral from a and b from -1 to 1, and the weight function is 1 minus x squared to the -1/2. Okay. Now, there's something that I've glossed over here, and that is this. I've called this quantity beta j squared, but I've given you no reason to believe that this is actually a positive number. Now we can see the denominator is positive because what you're doing here is you are taking the integral of the square of pj minus 1. So that's going to be positive. But what about the numerator? How do we know that this is positive? So I'll show you. Okay, so I'll just manipulate this. Same thing. All right. Well, first, I'm going to rewrite the denominator as, because it's an inner product of something with itself. So that is the 2 norm squared of that something. Okay. All right. So it's easier to see that this is definitely something that's positive, because a norm is never 0 unless the thing you're taking a norm of is 0, which this is certainly not. Okay, what about the numerator though? So I'm going to take the x and move it over here. Now, this part, xpj minus 1, what's the degree of that?
Is it 2?
Sorry, what?
Is it 2 because of the 3 terms?
No.
No, okay.
What's the degree of each pj minus 1? Or each of these p's? It's not going to be a specific number, it's a variable.
Is it just j, since you have j minus 1 and then you add 1 for the x?
Yeah. So here we have 2 polynomials of degree j we're taking inner product of. But if I look at xpj minus 1, we've seen that up here. So xpj minus 1 is pj with other terms subtracted off. So what I can say is, okay. So this is equal to so xpj minus 1 is equal to pj plus those other terms. But what about those other terms? Let's take a look. It's these. All of these are multiples of other p's of lesser degree. So pj is going to be orthogonal to those other things anyway. So in fact, the inner product of pj with those terms will be 0. So it makes no contribution. So really what we have is just that. That's the inner product of pj with itself, which can be expressed as the norm of pj squared. That's why we know that this is a positive number, so we can write it as a beta j squared. I mean, that's really a notational convention. It could have been written, we could have called this anything, but it turns out to be convenient for other things to take this expression and call it beta j squared instead of just beta j. Yeah. So all you have to do to compute these orthogonal polynomials, you start off with P0 being equal to 1. And then you generate these alphas and betas, and then you can form the rest of your orthogonal polynomials. Now, we do need initial conditions. Well, I already gave one of them earlier. P0 of x is 1. And then P minus 1 is equal to 0, just so we can use this free term recurrence starting from j is equal to 1. Because if j is equal to 1, then we have P0 here, which is fine. And then we have P sub minus 1. But all it means is for j equals 1, you don't have this term. And then starting from j equals 2, then it gets introduced. All right, so questions about what happened here? And trying to see orthogonality is a wonderful thing because it makes so many things go to 0, simplifies formulas to an astounding degree. So yeah, maybe it's paying to generate just orthogonal polynomials, but then it makes so many other things easier once you have them. Now, I just realized that this has taken up most of class time, which is kind of unfortunate, but okay. All right, what I'm going to do here is I'm going to shift to highlighting certain things from a book. Okay. Just so I can shift back and forth. Okay, so here I mentioned this family of polynomials last time. I didn't really say anything about them. The Legendre polynomials are described here. So in this case, our interval of interest is -1 to 1, and then a weight function is just 1. So what you get after applying that free term recurrence is this sequence of orthogonal polynomials, the Legendre polynomials. So we start out with 1, and then the next one is x, and then the free term recurrence. So this is equivalent to the free term recurrence that I just showed you. It's just these are just normalized a little differently. Like the ones I showed were monic, but these have a different normalization. Like these are not monic because we have this fraction here. Leading coefficient is 2j plus 1 over j plus 1 times whatever leading coefficient Lj had before. But notice here I have x times the previous polynomial. Whereas in the general free term recurrence, I had x minus alpha j times the previous polynomial. So what that tells us is that for the Legendre case, all the alphas are 0. And this coefficient here plays the role of a beta j squared. It's not exactly equal to that because, again, the Legendre polynomials are normalized differently. But this will help you generate them. And this is a way that keeps numbers nice. And we will see Legendre polynomials later when we talk about Gauss quadrature. Because the roots of these orthogonal polynomials give the abscissas or the nodes for Gauss quadrature. So that'll be a topic for next chapter. So this is one of the best known families of orthogonal polynomials. In this example, all I did here was I'm approximating a function cosine on -pi/2 to pi/2. Now, Legendre polynomials are for the interval -1 to 1. So all I did here was I took the regular Legendre polynomials and I made a change of variable. So if these are for -1 to 1, I let x be equal to 2t over pi. So if t is from -pi/2 to pi/2, then x is from -1 to 1. So now I get these scaled Legendre polynomials that are orthogonal on -pi/2 to pi/2, and I use these to approximate cosine by a quadratic. So what happens here is, if I want to approximate cosine, I compute these inner products. This is a formula that I showed you earlier for the coefficients, and that means evaluating these integrals, where f is equal to cosine, and then the LJ tildes are my orthogonal polynomials. So here I compute all the required inner products to get my coefficients. So this is my approximation. F2 is approximation of cosine. That's a linear combination of these modified Legendre polynomials. So once I get the coefficients that are given here, then I can get my quadratic approximation. Now, you're already familiar with a quadratic approximation of cosine. That's the first two terms of its Taylor series. But this is a very different polynomial that's meant to satisfy different criteria. And here it agrees fairly well with cosine. It doesn't really match it here, but it's pretty close. But the point is, this is an approximation that is best on the whole interval -pi/2 to pi/2 by minimizing the 2 norm of this deviation between them that you see. I think these are homework problems that I did not assign, or I might have assigned one of them. Okay, Chebyshev polynomials. Those are also orthogonal from -1 to 1, and this is a weight function. So orthogonality has to be defined with respect to a certain inner product. That inner product has to be specified. So which interval AB, which weight function W of X, if there is one. Okay, and this is the old material on Chebyshev polynomials that you've seen already. But what's interesting is when you're computing inner products of f with a Chebyshev polynomial, like you see here, and you include the weight function, then if you make a u substitution in the integral, x is equal to cosine theta, then this Chebyshev polynomial just becomes cosine of j theta, and the integral simplifies considerably under this change of variable. So in fact, you could do what is called a discrete cosine transform, not of f of x, but rather f of cosine theta. So it's kind of like a warped version of f, and you can get your inner products very quickly that way. Okay. All right. Here we have a very important theorem about orthogonal polynomials that I'm too lazy to type, but also we're low on time. So Fn that I've defined, well, here it is defined to be the best 2 norm approximation by polynomial degree n of f. So it's constructed that way. And notice here we have the same inner products, but notice there's no denominator. And the reason for that is these polynomials, q0, q1, etc., are said to be orthonormal, meaning the inner product of each one with itself is equal to 1. This is a Kronecker delta that I've showed you before. This expression is equal to 0 when j is not equal to k, and it's equal to 1 when j equals k. So, so here, this is the same formula that I showed you earlier. In fact, I'll jump to it. So it's approximation of this form where the coefficients, the CJs, are given by this formula, but now this inner product is equal to 1. All right, so that's how we get this. Now, so what does this theorem say? The theorem says that this polynomial that's defined here is the best approximation to f of degree n if and only if the error f minus fn is orthogonal to all polynomials of degree n or less. So problems 12 and 13, which I assigned in the homework, are meant to prove the two parts of this theorem because it's an if and only if situation. So in problem 12, you're asked to assume that f is defined this way, and you show that this is satisfied. So what that means is, so I'm going to give preemptive hints. So what you would do is you would take this formula for fn and substitute it in here, and use the various properties of the inner product to simplify things. And what you could do is you want to show that it's equal to 0 for any p of polynomial degree n or less. But what you can do is you can set p equal to any one of these q's, like set to a generic like qk, and show that this must equal 0. Why does that work? Because you want to show that this inner product is 0 on this entire space. It's sufficient to show it's equal to 0 for p coming from a basis. And q0, q1, q2 up to qn is a basis for this space. So you show that it's equal to 0 for p equal to each member of a basis, it must be equal to 0 on the entire space. So if you use p equal to some generic q, like I said, qk, then you can use the fact that these are orthonormal and all the properties of the inner product to show that this is 0. The other part, this problem here, there's different ways of doing this. I've actually seen this done in another textbook, but I came up with a different way. And what do you want to show? And I actually did something like this in the section on linear splines, so you can consult the notes there. You want to show that this expression, f minus p, where p is any polynomial of degree n, is equal to this, or like show this squared is equal to this squared plus something that has to be positive. Here, you're assuming that this is 0 for any polynomial of degree n, and you want to show that this is true. So if you use the approach taken to show that the piecewise linear spline is the flattest function, like the manipulations that I did there with inner products, you can use those here too, to show that this square is equal to this squared plus something positive. And then you take advantage of this. And note the hint I gave here. F minus fn is orthogonal to any polynomial in Pn. So if you're working with these, you might get an expression kind of like this, but it doesn't have to be p here, like not literally p, It just has to be any polynomial that is known to be of degree n or less. And you could say, oh, that's 0. So that's something important to take advantage of. Okay. Last 2 minutes. A very interesting aspect of orthogonal polynomials. Because polynomials of degree j normally have up to j roots, but the roots might repeat or the roots might be complex. But what's known about orthogonal polynomials is that the roots are real, they're guaranteed real, they're also guaranteed to be distinct, and they fall within the interval AB. And that's proven down here for all the different cases. And that is going to be very helpful to us later when we want to use roots of orthogonal polynomials for purpose of approximate integration. Because we're trying to approximate an integral on the interval AB, and we want to evaluate the integrand at points within AB. So knowing that the roots of these orthogonal polynomials will lie within AB is very helpful, because that means that those roots are viable choices of points to evaluate your integrand at. But it's just really interesting that polynomial roots could behave in so many different ways, but if you have polynomials that are orthogonal, then this must happen. Now, you've actually already seen this. You had a homework problem to prove that this is true for Chebyshev polynomials, which are orthogonal polynomials. Roots are real, distinct, and lie in -1 to 1, the interval where they're orthogonal. So that turns out to be something that is true in general. Okay. What I will do when I post these notes, since I was going through things in the book here, I will write into the notes the key points that I've just made here, just so you have that in writing, not just me blabbing it. Okay. Well, it's now 5:15, so I have to wrap. Come on. But I'll stick around in case anyone has any questions. But officially class has ended. Okay, well, Caleb's already gone anyway. Okay. Oh, we're all gone.